Okay, uh, welcome back to the Physics 232 video lectures. This, in fact, will probably be the last video for this course, so I hope you've enjoyed them. What we were talking about in the previous video was just a general discussion about how photomultiplier tubes are able to detect single photons. And they do this through the use of the avalanche effect, where a photon coming in creates a single electron via the photoelectric effect, and that electron is accelerated to a metallic plate using a potential difference from a high voltage power supply. And it gains enough kinetic energy that when it collides with that plate, it creates secondary electrons. So then the original plus the secondary electrons are accelerated to a second metallic fin or plate called a dynode. And all of those create more secondary electrons. And you can have as many stages of this as you like, so that by the time you get to the final anode, you have hundreds of thousands or millions of electrons that create a little current pulse that you can detect every time a single photon creates a single photoelectron. And so it's a very nice way of getting a high sensitivity detector. What we're able to do in our analysis of the photomultiplier tube is say, for a given number of incoming photons, we were able to calculate the average number of electrons that would be expected at the anode of our photomultiplier tube. And we did this just using some basic probability theory. So, for example, the binomial distribution would tell us how many of the photons would actually create photoelectrons, which then go through the different stages of the dynodes and create the secondary electrons. And so that was all nice. And so we could say the previous analysis allowed us to calculate the average number of electrons expected at the anode for a given number of incoming photons. What it didn't tell us is what would the distribution of the number of photons arriving at the anode look like. So, for example, if we had 8 photons come in and hit our photocathode, and then we count the number of electrons at the anode, and we did that over and over and over, so we always send in 8 photons at a time, and then we just keep track of, for each trial, how many electrons do we get at our anode. What would the shape of that distribution look like? What would the tail look like for, say, high number events where we get lots of photoelectrons, because maybe in certain cases a lot of the incoming photons actually produce an electron that gets accelerated through the chain of dynodes. Or how does it look at the low end, where if the quantum efficiency is low, then we expect that usually we don't get a lot of photoelectrons generated by the incoming photons. And so how does the low number of anode electrons, how does that part of the distribution look? And so what we're going to try to do is we're going to try to construct a little simple computer simulation to see if we can uncover some of the features of the distribution of final electron numbers at the anode. I'm by no means a Monte Carlo expert, and so I don't want to pretend like this was a simulation that I invented on my own. It's not. I found this simulation discussed in another course that had some online notes, and when I show you the code, I'll actually show you the original URL where I found a discussion of the photomultiplier tube simulation that we're going to try to reproduce. Okay, so the question is, what does the distribution of the number of electrons arriving at the anode look like? i.e., how does n vary when we repeat the same experiment over and over? And so by the same experiment, what I mean is we always send in the same number of photons. Every trial starts the same, and then we just look at how the number of final electrons at the anode varies. Okay, so if you think back to kind of our first simple Monte Carlo simulations, one was an attempt to calculate pi by spraying random dots onto a square and seeing how many of them land within the circle that fits inside that square. And so the way we solved that problem was by drawing random numbers from a probability distribution. So the points that we sprayed were associated with some probability. And then we did the same sort of thing for trying to integrate a complicated function. So we, again, just sprayed points, and we looked for how many of those points fell beneath our function compared to the total area of a square that contained the function we were trying to integrate. So that's always a feature of a Monte Carlo simulation. We want to be able to associate a probability distribution with some feature of the problem we're trying to solve. So if we think about the problem that we have, on average, we get 7.5 secondary electrons at each dynode. And so remember, this was assuming that the voltage required per secondary electron was 20 volts, and the voltage difference between adjacent dynodes was 150 volts. So that 7.5, where that number comes from, is the 150 divided by 20. So we give each electron, if we give an electron kinetic energy equal to the electron charge times 20 volts, then that's enough to create a secondary electron. And so if we give it 150 volts, that's enough to create 7.5 secondary electrons. If you remember, in our original photomultiplier tube, we had 6 dinodes, and we had 150 volts between the first 5. And so in all those cases, we would get on average 7.5 secondary electrons per incoming electron. And then between the second last and the last dynode, for some reason we set it to be 100 volts, and so we'd only get 5 secondary electrons in that case. Okay, so and we use that number to calculate the average number of total electrons at the anode. However, you don't always get seven and a half secondary electrons per incoming electron. Sometimes you get fewer. So sometimes maybe a single electron accelerated through 150 volts results only in 5 secondary electrons. Sometimes you'll get more, right? Maybe sometimes you get 12 secondary electrons produced. And so there's some variability in the number of secondary electrons per collision. The distribution of secondary electrons let's say the distribution of secondary electron number should follow a Poisson distribution. So if you remember, we had our Poisson distribution, which we found was useful in situations where we had to do counting. I think the example we used was counting, say, the number of muon decays in a certain time interval. And so here we're counting the number of secondary electrons produced during a collision at a dynode. Okay, and so what we can do is, in our simulation, instead of always getting 7.5 electrons for each incoming electron hitting the dynode, we can draw a random number that follows, well, we can draw a number from a Poisson distribution that has the right average value. Okay, and so we'll see how we implement that. And so the question is then, how does this randomness affect the number of electrons collected at the anode? And so that might be a legitimate question if you're designing photomultiplier tubes as particle detectors in some critical experiment. And so what we're going to do is we're going to set up a Monte Carlo simulation to try to address that question. Okay, so here's the structure. Of the Monte Carlo simulation. So one is, we first suppose that we have NP photons incident on our photocathode. And so we have to determine first how many of those photons actually create a photoelectron, and that's determined by the quantum efficiency of our photocathode. So what we're going to do is, for each photon that's coming in, so if we have 8 of them, we're going to do this 8 times. We generate a random number, let's call it x, from a uniform distribution that has the range 0 to 1. And if the value of x drawn is less than the quantum efficiency, which is, say, 0.23, then we say a photoelectron is produced. And what we would do is we would say, okay, let's start with 0 photoelectrons, and then if we have an x that's less than the quantum efficiency, then we say the number of photoelectrons is incremented by 1. And we'll put this inside of a loop. And so if the number of incoming photons is 8, our loop will run from 1 to 8, and we could get anywhere from 0 to 8 photoelectrons produced. So after all NP of the photons are considered, we know the total number of photoelectrons that will be incident on the first dynode. Okay, so that's step 1, is basically just to we already introduced actually some probability and some randomness by having the number of photoelectrons determined by numbers drawn from a uniform distribution. Okay, so 2. So our photoelectrons hit the first dynode. On average, each one of them, maybe we should say each photoelectron creates, let's see, V1 minus 0 over 20 volts secondary electrons. And so if you remember in our picture of our photomultiplier tubes, the voltage of the photocathode was the photocathode was attached to ground. So photocathode voltage is 0, and this V1 is the voltage of the first dynode. Okay, so therefore what we should expect is that the average total number of secondary electrons at the first dynode should be, well, it's the number of photoelectrons that are coming in, and then the number of secondaries for each one of those should be the dynode voltage divided by 20. So if it's 150 volts divided by 20, it's 7.5 secondary electrons for each of the incoming photoelectrons. And so what we're going to do is we're going to use that as the mean mu in our Poisson distribution. So we will use mu as the mean in our Poisson distribution. Okay, and so one thing to just notice is that every time we run the simulation, right, if we repeat it, 10,000 times, then mu is going to change for each iteration, because in each iteration we might get a different number of photoelectrons coming in, right? Because we send in 8 photons, and sometimes we might get 6 photoelectrons, sometimes we get 4, sometimes we get 3, and so that's going to make the value of mu, the average number of secondary electrons, change. Okay, so that's the average number, but we won't always get exactly mu secondary electrons. The actual value is determined by Poisson distribution. And so let me remind you of what that distribution looked like. So the Poisson distribution had 2 parameters. One was x and one was mu. So mu is already the mean that we calculated above. And what the Poisson distribution calculates is, maybe it's better to do it like this. The Poisson distribution calculates the probability of obtaining the value x when the mean is mu. Okay, and so if you recall, the form of the Poisson distribution was mu to the power x divided by x factorial times the exponential of minus mu. Okay, so what we're going to do is we're going to use Maple or whatever mathematics software you like. It could be MATLAB or Python or anything else to generate. We're going to use the software to generate a random number. Let's call it ND1. So ND1 is going to represent the number of secondary electrons at dynode 1. And this random number is not going to be drawn from a uniform distribution, but it's going to be drawn from a Poisson distribution with mean mu is equal to the number of incoming photoelectrons times the dynode voltage divided by 20 volts, which was the voltage required to make a single secondary electron. And so this notation ND1 is the number of secondary electrons at the first dynode. Okay, good. So now what we would have is the total number of electrons leaving the first dynode is the original number that were coming in plus the number of secondaries that were generated, leaving the first dynode and going on to the second dynode is, so the number of electrons is equal to the number of photoelectrons that were originally coming in from the photocathode plus the number of secondary electrons which was generated from the Poisson distribution. So this is the incoming electrons from the photocathode, and this is the secondary electrons generated at the dynode. It would be dynode 1 in this case. Okay, so after that, what we would do is we would repeat step 2 for all dynodes. Okay, so for example, what we would say is that, let's call this the number of electrons 1 leaving the first dynode. Okay, so then for the second dynode, what we would do is we would say mu is going to be updated. So it's going to be the number of electrons that were leaving the first dynode, which is more than the number of original photoelectrons that were created. And then we would say we would take the voltage of the second dynode minus the voltage of the first dynode, and then we would divide by 20 volts, the average potential difference required to create a single secondary electron. And so we would use the updated mean in the Poisson distribution for the second dynode. And so what we would do is we would say, okay, we're going to draw a number from a Poisson distribution with a mean equal to this value. And so that number represents the number of secondary electrons. So that number gives the secondary electron value, the secondary electrons, which would be ND2, the number of secondary electrons from dynode 2. Then the number of electrons leaving the second dynode would be equal to the number of electrons that were coming in, which are the ones from the first dynode, Ne1, and then we would add Nd2, and then we would continue. We would update the value of the mean for the third dynode. It would be equal to Ne2 times V3 minus V2 divided by 20 volts. We would draw a number from a Poisson distribution with that mean. That would be the number of secondary electrons from the third dynode. And then we would update the total number of electrons as Ne2, the original number that were coming in, plus that number of secondary electrons. And we do this until we completed all dynodes. Okay, so after completing for all dinodes, we would have the total number of electrons arriving at the anode. Okay, but that's not exactly what we wanted. We wanted to know what the distribution would look like. So all of this was just for one trial of the simulation. The third step is to repeat. This would be step 4. Step 4 would be to repeat steps 1 to 3 many times, and then we would plot a histogram of the number of anode electrons, and that's the distribution that we were originally trying to find. Okay, so that's the strategy. What I'm going to try to do is I'm going to show you an implementation of this in Maple, and this Maple code and the PDF of the Maple code will appear on the course website. Okay, so let's try this out. Let's see if we can make this work. So I need to find Adobe, and so here it is. So Monte Carlo Photomultiplier tube simulation. I said that I was not the one who created this simulation, and so there is, here we go. Let's see if I can turn on a pen. Oh, yes. Okay, so the original URL where I found this simulation is right here. I did check this link before making this video, and as far as I can tell, it's not active anymore. And I tried to search for an updated link with the same information, and I couldn't find one. Nevertheless, the person who did it was, I guess, McGrew. Okay, so in the simulation, here's the first thing that we try to do is to generate a random number between 0 and 1 drawn from a uniform distribution. So a uniform distribution just means that no one number is more likely than another number. And so here's just the syntax for doing that in Maple. So it's random number from a uniform distribution between 0 and 1. And I just called that function x so that when we call x, it spits out one random number. It happened to be 0.39. Now, if this was done in the simulation, we would say that's a number that's bigger than our quantum efficiency of 0.23, and so that particular incoming photon would not have generated a photoelectron. Okay, and so here's just a test, and so the test is let's draw random numbers. So here's that function x, 2,000 some odd times, and let's just count every time we have x less than the quantum efficiency of 0.23. Let's just increase the number of photoelectrons by 1. And when I ran this 2,363 times, what I found is that we got 537 photoelectrons, and hopefully 537 divided by 2,363 is a number that's close to 0.23. Okay, so this was just a test that our uniform distribution was working properly. This is not the Monte Carlo simulation yet. Okay, so the next thing to do is to generate a number drawn from a Poisson distribution. And the syntax is similar to what we had above for our uniform distribution, just instead of putting a uniform distribution in there, we just put in a Poisson distribution, and then we have to specify a value for the mean. And so here's another test where I'm going to set the mean equal to 2000, and we're going to draw random numbers from the Poisson distribution 1,000 times, and then just plot a histogram of that. And so there's the histogram, and you can see that the average is right around 2,000, and so that makes sense. Okay, so, and the distribution for averages that are much bigger than 1, we expect that distribution to look reasonably symmetric. It should approach actually a Gaussian distribution, and it looks like it's done that. Okay, so here's the photomultiplier tube simulation. I wrote here some comments at the beginning that if you want, you can read carefully. I also tried to, all of the red text in here are comments about what each line of the code is doing. And I tried to be overly detailed with the comments. So you can read through those if you like. So the first thing we're going to do is, I think we're going to send in just a single photon. Okay, I think that's what's going to happen. And so the first step is to set the quantum efficiency, and we set it to be 0.23. This max I is the number of times we're going to run the simulation. So we're going to send in a single photon 10,000 times, and we're just going to plot a distribution of the final number of electrons collected at the anode. And here is just a list of the dynode voltages. So the photocathode starts at 0 volts, dynode 1 is at 150, 2 is 300, 3 is 450, 4 is 600, 5 is 750. Those all incremented by 150. And then the last one, 6, increments just by 100, okay, to 850. Okay. So here's the first step is we're going to run this loop from I to max I, and so that's 10,000. So 10,000 iterations. And here we draw our random number. So this is a random number between 0 and 1, and we just check if it's less than the quantum efficiency. If it is less than the quantum efficiency, then we say that we created an electron. If this condition fails, so x is greater than the quantum efficiency, then we just go all the way to the end of the loop and nothing happens. Okay, when we do create an electron, what we're going to do is we're going to go from the first dynode to the last one, and we're just going to we're going to set the value of mu, the mean of our Poisson distribution. So if there's one electron, we have 1 times the dynode voltage, which would be, for the first case, it would be 150 minus 0 divided by 27.5. And then we draw a random number. This is the number of secondary electrons. And we add that to however many electrons were initially coming in. So if we're sending in just one photon, for the first dynode, the number of electrons is just 1. And we add to that the secondary electrons. And then we go back to the top and we say, well, let's update the mean of the Poisson distribution because we changed the number of electrons. And then we draw a random number from the Poisson distribution with the new mean, and we get the number of secondary electrons at the second dynode. And this goes all the way until we've done this for all 6 of our dynodes. Okay, and then we're just going to say, okay, after that finishes, we just have the number of anode electrons, and we're going to add that to a list. And when we plot the histogram of that list, this is what it looks like. And if you remember, we calculated an average value of about 300 and... No, what was it? It was 266,000. So this is where we calculated the average. And you can see it's not right at the peak. The peak is at 250. It's just that the tail here for high numbers of photoelectrons is longer than the tail here for the low number of anode electrons. And in fact, when we calculate the average we just take all the anode electron numbers that we got for our 10,000 trials and find the average, we get the 266 times 10 to the 5 times 10 to the 3, I guess, that we calculated. Okay, but so here's information that we didn't have before. We didn't have the fact that we had an asymmetric distribution with a longer tail for large numbers of anode electrons. So this is the same plot on a log scale. So it's a log scale on the vertical axis. Okay. Here's the same code with just one additional feature added. That one additional feature is that we're not going to send in one photon, we're going to send in 8 of them. And what's different is that now there's an extra loop in here. And what does that extra loop do? It draws a value of x for all 8 of our photons. Number of photons is 8. And so every time you draw a value of x that's less than the quantum efficiency, we increment the number of photoelectrons. So it started at 0. And if we draw x less than 0.23, we increment the number of photoelectrons. After that, everything else is exactly the same. So all of this is the same as what we did before. We're just starting with different numbers of photoelectrons generated from the 8 incoming photons. And then when we plot the distribution for that case, then the average we get is, remember we calculated about 500,000, and so we get that same average, and that's over here. And this time, the tail, the high number of anode electrons tails is really long compared to the tail for a low number of anode electrons. And so now we're starting to see some of the details of that distribution. And so that's one thing that we could write a relatively simple Monte Carlo code to do for us when that might not be a trivial thing to just calculate on pen and paper. Okay, so that's it. Like I said, this example code will be put onto the course website. I hope you enjoyed the course, and I hope that these video lectures worked out for you when they had to be thrown together at the last minute. And with that, I'll be signing off. Thanks very much. Bye.